is eigenvalue of, since lambda is eigenvalue of A, we have Ax equal to lambda x. Take this as equation 1. Ax equal to lambda x. What we have to do to this pre-multiply equation 1 by matrix A. Then 1 implies, what is this? A into Ax equal to A into lambda x. Since matrix product is associative, I can write like this. This lambda is the scalar, I can write anywhere. So outside this one, using associative property, using associative law. Then A into A square is there. Okay. Then this implies A square into x equal to, I will write lambda into, what is Ax? From equation 1, what is Ax is nothing but lambda x, using equation 1. What is the change? This Ax is replaced by lambda x using equation 1. Okay. Then what this gives? This implies A square x equal to lambda square x, equation 2. So what this indicates? Lambda square is eigenvalue of A square. Lambda square is an eigenvalue of A square. Okay. Next one, pre-multiplying equation 2 by A. Then what this is? A into A square x equal to A into lambda square x. Again same logic, using matrix associative property. A into A square x equal to lambda square into Ax. That implies this is A cube x equal to lambda square into lambda x. This is again same, Ax equal to lambda x using equation 1. So that gives what? A cube x equal to lambda cube x. This is equation 3. That is, lambda cube is eigenvalue of A cube. Proceeding in this manner, we conclude that lambda power m is an eigenvalue of A to the power of m. This is one method. And for example, the question may be like this: if lambda 1, lambda 2, and so on, lambda n are the eigenvalues of A, then lambda power m, lambda 2 power m, lambda n power m are the eigenvalues of A power m. What is this? Not single eigenvalue. It is what? Lambda 1, lambda 2, lambda n, lambda 1, n eigenvalues are there. Then how to prove this one? Same procedure, but the change is here. If lambda I equal to 1 to n eigenvalues are the eigenvalues of A, then we have, what is actually, if lambda is eigenvalue of A, we have Ax equal to lambda x. Now 1 by 1 eigenvalue. So this is lambda I. For lambda 1, eigenvector is x1. For lambda 2, eigenvector is x2. Therefore, this will be I xi lambda xi. This is I equal to 1 to n. That is the change. That's it. Remaining everything is same. Next is what? Pre-multiplying by a. Pre-multiplying by a. Exactly same above proof. Okay. So this is a into a xi equal to lambda into a xi. Okay, what is axi value from equation 1? Lambda xi, and this is what? A square xi equal to lambda I into lambda I xi from equation 1. From equation 1. So what is this gives? A square xi is nothing but lambda I square xi. What this shows? This implies lambda I square is lambda I square for what? I equal to 1 to n are eigenvalues of a square. So in general, proceeding in this manner, that's enough. Proceeding in this way, we can conclude that lambda I power m I equal to 1 to n are the eigenvalues of a power m. Eigenvalues of a power m. Okay, this is one more property. And another one. Any square matrix A and its transpose have the same eigenvalues, Okay, for this proof, in matrices we have, what is this? Determinant of B equal to determinant of B transpose, correct? Right now, if we consider one matrix B and it's a B transpose, both determinants have same. Okay, B equal determinant of B equal to determinant of B dash. Now, determinant of B dash. Now, why Sujit Reddy? Now, this is B equal to B transpose. Next one, what we have, see, any square matrix A and A transpose have same eigenvalues, have to prove. Okay, we derive eigenvalues using the characteristic equation. Using what? Generally, characteristic equation. What is that characteristic equation? Determinant of A minus lambda equal to 0. We derive eigenvalues of A using characteristic equation, determinant of A minus lambda equal to 0. Okay, similarly we get eigenvalues of A transpose by solving the characteristic equation. What is that? In place of A transpose will be there. That's it. Okay, and what will happen here? Equal to 0. This is, take this as 1 and take this as 2. Okay, since determinant of B equal to determinant of B transpose, okay, equation 1 and equation 2 gives same eigenvalues. Therefore, A and A transpose have same eigenvalues. values. Okay, this is one more property of eigenvalues. And next one, what is that? Yeah, you take this. This is important. The sum of eigenvalues of a matrix. The sum of eigenvalues of a matrix is the trace of A. Is the trace of A. What is the meaning of trace of A? Sum of diagonal values and product of eigenvalues. Product of eigenvalues is determinant of A, or is equal to determinant of A. Is equal to determinant of A. Okay, see the property. What is the property? Property is what? Sum of eigenvalues is equal to what? Trace of A, and the product of eigenvalues equal to determinant of A. Proof. How to prove this? Let me consider to prove this. Okay, to prove this property, is voice is clear?
Yes, sir.
To prove this property, let me consider in an easy manner 2 by 2 matrix. Okay, to prove this property, let us consider a 2 by 2 matrix. A 2 by 2 matrix. What is 2 by 2 matrix? General representation: A equal to 1 1 position, 1 2 position, 2 1 position, 2 2 position. Okay, based on this property, there are many questions asked in gate examination. Okay, so this property is very important. A11, A12, A21, A22. Okay, then what happened? I have to find eigenvalues first, right? So characteristic equation of A is determinant of A minus lambda I equal to 0. So what this gives? Determinant of A minus lambda I, determinant of A11 minus lambda. From diagonal positions, I have to subtract lambda. That's it. A21. This is equal to 0. Now, let me expand this. A11 minus lambda, A22 minus lambda, minus A12, A21 equal to 0. Equal to 0. Let me take product. A11, A22 minus A11 plus A22 into lambda quotient. If I take common, lambda square minus A12, A21 equal to 0. So what is this? Gives quadratic equation. Since 2 by 2 matrix is there, characteristic polynomial is of order 2. Lambda square first minus A11 plus A22 into lambda plus A11 A22 minus A12 A21 equal to 0. This is equation 1. Got it? Is a quadratic equation. Is a quadratic equation. Let lambda 1, lambda 2 be the roots. Roots, nothing but eigenvalues. Be the roots, eigenvalues of equation 1. Everyone getting what I'm considering? Once again, to prove this property, sum of eigenvalues is equal to sum of the diagonal elements, and the product of eigenvalues equal to determinant of matrix A. I'm considering one 2 by 2 matrix. First, let me find eigenvalues. For this, I am considering characteristic equation, right? And I'm substituting expanding characteristic equation. I got one quadratic equation. This is the quadratic equation. And what are the roots of quadratic equation? Since it is quadratic, I'm taking lambda 1, lambda 2, which are nothing but eigenvalues. And what is clearly sum of roots? Sum of roots, nothing but what? Lambda 1 plus lambda 2. What is the property? You know this, ax square plus bx plus c equal to 0. Then sum of roots is what?
Minus b by a.
Minus b by a. This is the property. So what is this? This is a value is 1 here. B value is what? This one. So what is this? A11 plus A22. Got it? Anyone? Any doubts? That is lambda 1 plus lambda 2 means what? Sum of eigenvalues. Eigenvalues equal to what? Sum of diagonal elements. Sum of diagonal values. Nothing but trace of A. First property is over, right? Coming to another one, product of roots. This one is over. Next one, product of roots. Product of roots means that is lambda 1 into lambda 2 equal to what? C by A. Do you remember what is this? I'm writing here, product of roots equal to C by A. What is C here? This is the C. C by A value 1. So what is this is A11 A22 minus A21 A12. So I can write this as A11 A12 A21 A22. Nothing but determinant of A. This is lambda 1 into lambda 2. That is product of eigenvalues. Product of eigenvalues equal to determinant of A. Product of eigenvalues equal to determinant of A. Got it? This is one beautiful property of eigenvalues and eigenvectors. Next one. Based on this, see how to tell. Yeah, let me try. First property, just I'm giving the previous gate questions. If all the eigenvalues are non-zero, what the eigenvalues are non-zero, then what is this? Then what we have, determinant of A is what? All product of eigenvalue equal to det A. All the eigenvalues are non-zero means determinant of A is what? Not equal to 0. Determinant of A not equal to 0. Why? Because what is this is? Since det A equal to product of eigenvalues. Product of eigenvalues. That is, if all the eigenvalues are non-zero, then A is what? Det A not equal to 0 means what? A is non-singular matrix. This is one bit. A is non-singular matrix. Next property. If determinant of A equal to 0, then at least one eigenvalue must be what? At least one eigenvalue is 0. At least one eigenvalue is 0. Okay. And similarly, how to write A inverse? A inverse exist means what? Det A not equal to 0. So using that one also, A inverse exists in brackets, det A not equal to 0. A inverse exists, det A not equal to 0. This is IFF means if and only if 0 is not an eigenvalue. 0 is not an eigenvalue of A. 0 is not eigenvalue of A. Okay. Next one. Another property. These are the properties based on the previous one. Now another one. Another property. If lambda is an eigenvalue of A, then I will write like this. Lambda I is an eigenvalue of A means many. Then lambda I plus or minus k, lambda I plus or minus k is the eigenvalue of that means lambda I plus k or lambda I minus k, eigenvalue of a plus or minus ki matrix, a plus or minus ki. This is one more. Next one, this is over. Yeah, this is also one more property. Upper triangular, lower triangular matrices, you write like this. No. For upper triangular, lower triangular matrix, eigenvalues are the diagonal elements. You write like this: upper triangular or lower triangular, upper triangular or lower triangular matrices for upper triangular or lower triangular matrices, eigenvalues are the principal diagonal elements. Principal diagonal elements. Okay, for this, that is just I'm giving hint. Upper triangular matrix means, for example, this is I'm taking 1, some minus 2, 3, and this is 2, some 8, minus 5. Below the diagonal, this is the diagonal, principal diagonal. This is called principal diagonal. If the below the principal diagonal, if the values are 0, this is called upper triangular matrix. This is called upper triangular matrix. For this, what are the eigenvalues? 1, minus 2, 3. 1, minus 2, 3. And coming to lower triangular matrix, same thing. What is the lower? If I take like this, minus 2, 3, some 8, some 9, okay, and this is something, whatever it is, negative 1, and above the diagonals, this is 0. Above, this is the diagonal, principal diagonal. Above the principal diagonal, the values are 0. This is called lower triangular matrix. Lower triangular matrix. Why 1, 2, 3 again? Let me take different ones. This is some minus 2, 5, some minus 3. Okay, this is the principal diagonal. Eigenvalues are minus 2, 5, minus 3. Okay, these are the properties of eigenvalues. Any doubts? And someone asked, eigenvalues are complex. Yes, eigenvalues may be complex also. Eigenvalues may be complex also. Next topic is Cayley Hamilton theorem. Cayley Hamilton theorem. Statement is what? Every square matrix. Statement is every square matrix satisfies its own characteristic equation. Its own characteristic equation. Its own characteristic equation. This is the statement. Okay. Every square matrix satisfies its characteristic equation. The hint is what? If A is an n by n matrix, order n by n matrix, then its characteristic equation is what? Then its characteristic equation is determinant of A minus lambda I equal to 0. Determinant of A minus lambda I equal to 0. What this is gives, this equation is an nth degree equation. Nth degree equation, correct? Since A by is n by n, if it is 3 by 3, you will get what? Lambda cube, cubic equation in lambda. Now n by n matrix, this is an characteristic equation is an nth degree equation. So it possesses n eigenvalues. Now this is an nth degree equation in which lambda is unknown, right? In which lambda is unknown. I have to find this, right? See, characteristic, a matrix satisfies its characteristic equation. A is known, I is known. Which is unknown? Only lambda is unknown. In place of lambda, if I put A, just a rough figure, if lambda equal to, if lambda I equal to A, lambda is unknown, okay? We cannot take lambda equal to A because lambda is the scalar, A is the matrix. So we cannot take lambda equal to A. So substitution is what? If lambda A equal to A, then what is the characteristic equation? A minus A equal to 0 is satisfied. Okay, therefore lambda is unknown. In which lambda is unknown? If I replace lambda by A, roughly it's a crude one, not exactly one, just for idea. Just this is idea only to remember. Proof is very different. Proof is not in syllabus. Proof is very different. If we replace lambda by matrix A, lambda by A, that is still I am giving, it is not exact one. We cannot replace lambda by A. Lambda I is replaced by A. But in problems we consider this lambda by A. If we replace lambda by A, then determinant of A minus lambda I equal to A minus AI, that is equal to A minus A equal to 0, satisfied. That means what? Every matrix A satisfies its characteristic equation. Every matrix satisfies its characteristic equation. Got it? And what is the use of this Cayley Hamilton theorem? Using this Cayley Hamilton theorem, we can find powers of A. Powers of A means A square, A cube, A power 20, like that. And we can also find inverse of a matrix. For example, let me tell one problem. See, find the characteristic equation, not characteristic equation. I have to tell one easy problem. Verify Cayley Hamilton theorem. Just wait. Right. Verify Cayley Hamilton theorem. Verify Cayley Hamilton theorem for A equal to, the matrix is 1 2 3 1 2 3 2 4 5 3 5 6 3 5 6, and hence find the inverse of A, and hence find A inverse. And in this one again one more question. Express A power 8 minus 11 A power 7 minus 4 A power 6 plus A power 5 plus A power 4 minus 11 A cube minus 3A square, minus 3A square plus 2A plus I as a quadratic polynomial. In A. as a quadratic polynomial in A and find it. This is the question. So first what I have to prove? Verify Cayley Hamilton theorem. First question. Let me write. First matrix A is what? 1 2 3 2 4 5 3 5 6 3 5 6. What is Cayley Hamilton theorem gives that? So I will write Cayley Hamilton theorem states that every square matrix satisfies its characteristic equation. Every square matrix satisfies its characteristic equation. Okay. What happened? Now, characteristic equation. Now, the characteristic equation of A is determinant of A minus lambda I equal to 0. Okay, let me find this determinant of A minus lambda I. That implies that 1 minus lambda, 2, 3, 2, 4 minus lambda, 5, 3, 5, 6 minus lambda equal to 0. Now, if I expand this, I'm not giving full length expansion, time taken. If I expand this, I'm getting lambda cube minus 11 lambda square minus 4 lambda plus 1 equal to 0. Is the characteristic equation. Okay, after expanding this determinant. Okay, now what is this? Cayley Hamilton theorem states that gives matrix A gives that matrix A satisfies equation 1. That is what? A cube minus 11A square minus 4A. Now this is 1 now. In place of 1, I have to write I. In place of A, I have to write I. This is the Cayley Hamilton theorem. Okay, we have to prove this. Verify Cayley Hamilton theorem means we have to prove this equation. Now that is our duty now here. So one by one. First A. What is A square? A into A. I need A square, then A cube, then everything substitute here. What is A square? A value is what? 1, 2, 3, 2, 4, 5. Next one, 3, 5, 6. This is 1, 2, 3, 2, 4, 5, 3, 5, 6. Problem is very easy, but time consuming. Cayley Hamilton theorem. That's it. Otherwise, problem is very easy. Definitely one question will be there in Cayley Hamilton theorem, essay question. And the product is 14, 25, 31, 25, 45, 56, 31, 56, 70. A square is over. Next one, A cube. Next one, A cube. A into A square. A cube is A into A square. So 1, 2, 3, 2, 4, 5, 3, 5, 6. Multiplied by 14, 25, 31, 25, 45, 56, 31, 56, 70. Okay, 70. Next, the product is what? 157, 283, 353, 283, 510, 636, 353, 636, 793, 793. This is a cube. Now, verification. What is the statement? A cube minus 11a square minus 4a plus I equal to, I will write here, equal to a cube 157, 283, 353, 283, 510, 636, 353, 636, 793 minus 11 into 14, 25, 31, 25, 45, 56, 31, 56, 70, 11a square is over, minus 4 into a, 1, 2, 3, 2, 4, 5, 3, 5, 6. This is over plus I. What is I value? 1, 0, 0, 0, 1, 0, 0, 0, 1. This is I. If I calculate everything this, what you have to get? Definitely zero matrix. Therefore, a cube minus 11a square minus 4a plus I equal to 0 is verified. That is, Cayley Hamilton theorem is verified. Cayley Hamilton theorem is verified. One is over. Next one, what is the next question? Hence find A inverse. What is the next one? A inverse. Now, to find A inverse, what is the characteristic equation? Characteristic equation gives a cube minus 11a square minus 4a plus I equal to 0. Isn't it right? Multiplying by A inverse, pre-multiplying by A inverse. So A inverse into A cube minus 11 into A inverse into A square minus 4 A inverse into A plus I A inverse into I equal to 0. So what is this? A square you will get, here 11a you will get, here you will get 4i, and here A inverse you will get. From this, what is A inverse? You will get minus A square plus 11a plus 4i. All matrices are known for you. A square, what is that A square value? 14, 25, 31, 25, 45, 56, 31, 56, 70 plus 11 into what? 1, 2, 3, 2, 4, 5, 3, 5, 6 and plus 4 into what? Identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, all these are. So what is A inverse? After simplification, you will get A inverse equal to 1 minus 3 2 minus 3 3 negative 1 2 negative 1 0. This is A inverse. Now second part is also over, finding A inverse. And next one, what is the next one? Express that big expression as a quadratic equation. Yeah, express this one as a quadratic equation. Okay, that is the next question. So what I have to do for this, I have to calculate first this A power 4. A power, already A cube is known, A square, A cube is known, A power 4 let me find. Okay, otherwise is there any possibility? Let me write the expression. What is the next one? Next expression is what? a to the power of 8. And what is this equation in terms of cube now? A cube minus 11a square. Yeah, I can simplify this in a different manner. A power 8 minus 11a power 7 minus 4a power 6 plus a power 5 plus a power 4 minus 11a cube minus 3a square plus 2a plus I, right? Okay, this is the expression. And this expression, in the first one, I will take a power 5 common. Up to what? Up to here, I will take a power 5 common. What is this becomes? A cube minus 11a square minus 4a plus I. And from this term onwards, okay, let me take a common. A cube minus 11a square minus 3a plus 2I plus I separate. And what is this expression from the Cayley Hamilton theorem? A cube minus 11a square minus 4a plus I. Exactly what is this value? 0. So this implies, okay, or equal to this equal to a power 5 into 0 plus a into a cube is there, 11a square is there, but here what is this? Minus 4a is there, right? So I am taking this is minus 4a plus I. What are the extra terms here? Plus a and plus I. These two are the extra. To get again minus 3a plus 2i, minus 4a plus a, minus 3a, I plus I, this one plus I. So this equal to, already this is 0, no need to write. A cube minus 11a square minus 4a plus I. And let us separate these two. A into a plus I plus I. And again what is this value? 0. So this is equal to, this value is 0, right? Now this equal to a into 0 equal to plus a square plus ai plus I. This equal to a square plus ai plus I is the required quadratic polynomial. It is the question. Convert it to quadratic polynomial is the required quadratic polynomial. And hence find it. And hence find it means what? Find the matrix value. This is a square plus ai means what? No need to write this a. That's it. Ai means a. A square plus a plus I. A square value is what? 14, 25, 31, 25, 45, 56, 31, 56, 17 plus a. 1, 2, 3, 2, 4, 5, 3, 5, 6 plus I 1, 0, 0, 0, 1, 0, 0, 0, 1. Got it? Okay. So what is this value finally? This equal to, if I add the same positions, what I'm getting? 14 plus 1, 15 plus 1, 16, 25, 27. This is 34, 25 plus 2, 27, 45 plus 4 plus 1, that is 50. This is 61, right? This is 34, you will get. This is 56 plus 5, 61. And this is 76, 77. This is the problem. Any doubts? Yes? Similar problem, assignment. Verify Cayley Hamilton theorem. Verify Cayley Hamilton theorem for the matrix. For the matrix A equal to 1, 4, just it's a simple 2 by 2 matrix. And anyway, it's a solved problem in textbook. And find its inverse. Find its inverse. Also express a power 5 minus 4a power 4 minus 7a cube plus 11a square minus a minus 10i as a linear, not quadratic, it is linear. Linear means first degree, linear polynomial in A. Linear polynomial in A. Next one. Another one. Find characteristic equation. Find a characteristic equation of A equal to 1, 1, 3, 1, 3, minus 3, minus 2, minus 4, minus 4, and hence find its inverse. And hence find its inverse. Next one. Same. Find a characteristic equation. Find a characteristic equation of A equal to 2, 1, 1, 0, 1, 0, 1, 1, 2, 1, 1, 2, and find A inverse. Also find the matrix represented by a power 8, 5a power 7, 7a power 6, minus 3a power 5, plus a power 4, minus 5a cube, 8a square, minus 2a plus I. 2a plus I. Next question. All are same. That's it. This is Cayley Hamilton theorem. Next one, after this Cayley Hamilton theorem, we have linear transformation, orthogonal transformation, diagonalization of a matrix. Next one, quadratic forms. Hardly 3 classes, 3 hours. The first unit will be complete. Any doubts? Yes, any doubts? Properties of eigenvalues finished.